We all love Stable Diffusion, we've all seen it, we all know how amazing it is, but one of the biggest problems with it is so massive and you need a pretty big GPU to run it, and it also takes a while to do inference on it. Well, what if we could make the Stable Diffusion unit smaller so that it is not only smaller and you can put it on a smaller GPU, but the inference speed is also faster, even though you may suffer from a little bit of a quality drawback. Uh, that would be, I mean, that would just be a good thing to do because maybe people with smaller GPUs aren't able to use the full Stable Diffusion, but they can use this distilled smaller Stable Diffusion. And that's what this paper proposes. It proposes something called BK-SDM, which compresses Stable Diffusion by kind of removing blocks from Stable Diffusion from the unit. So first, I'll just go through how diffusion works. I've done a video on Stable Diffusion, but real quick, I want to go at a high level about how diffusion works and how the unit kind of does its thing. So for a normal diffusion process, you have an image, and I'm going to draw a cat. There we go. So there's our cat picture, and we will call this x sub 0. This is our image at time step 0, and we can move to another time step by adding a little bit of noise in it. So this will be, say, x sub 1, and there will be, I'm not going to draw it in black, draw it in red. So there's a little bit of noise in here, and the noise at time step 1 is sampled from a Gaussian distribution, and you add a little bit more noise in the next step, and you keep going until you get to the final step where you have, well, I don't even need to copy the image. You have pure Gaussian noise. So at this step here, you have 100% Gaussian noise, and this will be, say, x sub t. So you have t steps in this Markov chain process where you start with some image, and at each step you add a little bit more noise until you get to a full Gaussian, where x sub 0 is sampled from your data distribution, so we'll call that d, whatever that may be. That's just some image from your data distribution. And x sub t is sampled from a normal distribution with mean 0 and variance 1. So at any time step t, where t is in between 0 and big T, you can have a scheduler. So this is alpha sub t will be our scheduler, and you can interpolate between x sub 0 and x sub t. X sub 0 plus 1 minus alpha t, x sub t. And instead of doing x sub t, I'll call this epsilon, where epsilon is the noise sampled from the normal distribution. So it's an interpolation between your original image and your epsilon. So alpha t at time 0 would be equal to 1, and alpha t at time big T is equal to 0. So your original signal gets corrupted as you increase the number of time steps. Now, what you do is you train a model to reverse this process. So let's say, so at any time step t, you train it to, well, the idea is that you train it to remove the noise at one time step. So in this image here, we have some noise, and you train a model, say p theta, which takes in the image at time step 1 in this case, and it takes in the time step t is equal to 1, and it will predict the noise in that image. Now, at a high level, that's what it does. There's a lot of other ways that you can do this process. So in the actual implementation, what you do is you take any image, so at any time step, so say at any time step t, so we have an image here, which is say x sub maybe t over 2. So this is somewhere in the middle of the process, x sub t, where t is somewhere in the middle of the process. You actually train the model to predict the original image, or you train the model to predict the noise in the image, and then you can skip all the way to x sub 0, but the initial prediction is going to be bad, so then you go back to somewhere in the middle of the process, and you keep alternating back and forth until you converge upon the initial image. So you don't actually predict one time step at a time. You actually want to train a model to predict the original image, or to predict all the original image and or all the original noise. Either way, it's the same. So that's how you do a diffusion process. It's just training a model to reverse this process, whether that's predicting one step at a time or predicting all steps at a time, and then going back to one of the intermediate steps to kind of make the image better. Now, Stable Diffusion does this kind of trick to make this better. So there's two problems with doing it this way in pixel space. First off, the features in image space are sparse, so it may be more difficult to do this diffusion process. And second off, it's also a lot bigger, so that means you have to have, whenever you're passing data through the UNet is going to have to do a lot more computations to do one step at a time. But what you can do is you can compress this to a latent space. So instead, we train this massive autoencoder that will take in an image and it'll output the same image. So it's just an autoencoder that's trained on a ton of data, a ton of image data. So in this case, it would take in our picture of a cat, and the encoder would output some latent, or it would output some of these latents, whatever that may be, and the latents corresponding to that image. And then you throw it through your decoder, and your decoder will output something that's very similar. So it'll be, I'll draw it again. So it's slightly different, but it's something very similar. And this is just a normal autoencoder. So you train this, and assuming you have a trained autoencoder, what Stable Diffusion does, apart from normal diffusion, is you take the latents of the image and you do the diffusion process on that. So you have these latents at time t, and this corresponds with x sub 0. Instead, for latents, we'll call this z sub 0, just for different notation. So we pass in x sub 0 into our encoder, and we get out latents at z sub 0. Now, what we do is we add a little bit of noise to these latents, and you can't really visualize it, but you add a little bit of noise, and this will give you z sub 1, and then you add some more noise until you get to z sub t. That is a terrible t. Z sub t. There we go. And you train a model to reverse this in the latent space, so this is z sub t. Z sub t. And you train a model p theta, where given z at time t and the time step, it'll reverse this process where it removes some noise. And it does this like your normal diffusion process, like was stated up here, except it removes noise from the latents. So then whenever you're sampling, you can the way you sample is you sample from a Gaussian distribution here, and you just give that to the model, and then it'll unnoise it to an image. But in this case, you sample from a Gaussian distribution, and then it unnoises it to some latents, and then you throw the latents through the decoder to get your image. So that's what Stable Diffusion does. Now, there's also the conditional information that Stable Diffusion has, such as text. So let's just look at how the UNet works in general. So the Stable Diffusion model, the Stable Diffusion model itself is a UNet. So you have this UNet, this magical UNet, which will draw by a box. And the UNet will take in some latents at time t, and you throw that through the UNet. And what the UNet predicts is the the epsilon at time t, where epsilon was our sampled noise. So basically, the UNet is predicting all the noise within our latents at whatever time t. So any time step in the middle of this process, the UNet is predicting all the noise within those latents. And this UNet is basically our entire model. But it's conditioned on two things. First off, it's conditioned on the time step, and the time step is just the kind of absolute positional embeddings within the attention is all you need paper. It's where you sample the sine and cosine waves and then throw that through the UNet. So you can get these positional embeddings from the time step, and you just throw that through the UNet. Now, it also takes in text information. So maybe if we're looking at this image here, it'll be a picture of a cat. Now you can't directly put this through the UNet because this is text information. So instead what you do is you put this through, say, clip. You can throw this through other models such as T5 or UL2, but we'll just say you throw this through the clip model. And the clip model will output some encoding of this text, which you can then throw the UNet into the UNet and condition some of the you can pass in this conditional information to guide epsilon t. If you don't have this text information, then obviously it'll just generate something random. But if you do have the conditional information, it'll guide it hopefully towards a picture of a cat. Now, this UNet is what we want to compress because that is literally the entire model, and the UNet is what we need to do several times here. The encoder decoder, we only have one stage to take the lanes and then convert that to an image. Maybe you have multiple stages if you want to do super resolution on the images, where you take the decoder and then you take the output of the decoder and then you throw that through another decoder, and then that makes it a larger image. But for now, we'll just say that there's one decoder, and like we don't need to compress the encoder decoder. We don't need to compress the autoencoder. We only need to compress the UNet because that's what's being done t times to get your output image. So what does the stable diffusion UNet architecture look like? Well, they have that in the appendix here. So this is what it looks like. So whenever you have your image at whatever your latents at whatever time step that is, you're going to throw this through some down blocks, and then you'll get out like a smaller set of latents, and then you throw those through some more down blocks, and that'll give you an even smaller set of latents, and so on. And then you throw this through, in this case they have 3, so you throw this through another set of down blocks, and then you get out some even smaller lanes, really small. And then you throw this through the middle blocks, and then you do some upsampling. So you have your normal UNet architecture where you take the outputs of the current level and you append that or concatenate that whenever you're doing the upsampling. And you upsample, so these will be our latents, and you upsample again. Then you get out your prediction. And then you throw this through maybe some other blocks here. And you get out your prediction. This will be your epsilon, where that's your noise. So you give it the latents, and then you get out your epsilon here, normal UNet architecture. Now, the thing about this is each of these down blocks and up blocks actually have conditional information. This is where you're passing in the text information. So your text information would be passed into the down blocks as well as the up blocks. So it would also go here and so on. I hope you get the idea where you're just the down blocks and the up blocks they're what make the unit architecture, and you put the conditional information through the down and up blocks. Now they have a flattened diagram here where you can kind of visualize how the Stable Diffusion architecture is working. So if we look, we have our latents here. This is RGBA, and the latents are 64 by 64. Now you blow the RGBA into 320 channels, I guess. That's what they use, 320. And the down block is composed of a residual layer, an attention layer, residual layer, attention layer, and then a convolution, where the convolution is it's a strided convolution. So you subsample your image. So you basically downscale your image to by a factor of 2 at each down block, and usually you increase your number of channels by 2. So you downscale it, and then you have another residual block, attention block, residual, attention, and then you downscale, and so on. Your middle block is also composed of residuals and attention layers, and then your up block is composed of concatenating the output of your down layer to the up layer, like was showed over here. And then you do residual, and then you do another concatenation, residual, another concatenation, residual. And the up layers are kind of, it's a lot more there's a lot of concatenations in between there, even within the up blocks, which is kind of interesting to look at. And yeah, and you just have a bunch of up blocks until you get your output noise, your predicted noise. So it's a pretty kind of simple architecture, like idea for the architecture. Now, I think it's interesting to look at exactly how they implement this. So the residual block is composed of 2 convolutions. So this is your first convolution, and this is your second convolution. So this is your time information, and your time information, they go from, so t is going to be your integer value, which maybe it's equal to 10. Maybe you're at time step 10. And then you take the Fourier features, or not the Fourier features, you take the absolute positional embeddings, so time embeddings corresponding to the number 10, like you would in the attention is all you need paper, where you would take the positional embeddings of, say, the 10th token in the sequence, and that would represent your time embedding. And they have a really large time embedding, so it's 1220, it's 1280. It's a vector of size 1280, so that's a total of 1280 different sine and cosine waves. And they throw this through a Silu layer and project it to to whatever the channel dimension is in here. Now, specifically these residual blocks need to they need to upscale the number of channels potentially. If we look here, we can see that this residual block will have to upscale the channels from 640 to 1280, this one here. So yeah, so that's important. And the way they do that is by doing that with the first convolution, where it upscales it from whatever input channels, so that would be 640, to the output channels, 1280. So the input here is whatever the features are at that current block. You throw that through a group norm, and then they use Silu. I guess that works well. And then you have your projection, which potentially has more channels. Then all they do is they just add the time embeddings. They don't do anything special. They literally just add it in the middle of the blocks. And then you have another group norm, a Silu, and another convolution. So each residual block is made of 2 convolutions like you would expect, but the time information is added in the middle. So this is pretty standard except for the Silus and the time embedding. Now, more interesting is the cross-attention block. So the cross-attention block is how it's how you're going to condition the information on the text. So the text from TLIP, if you take not the direct output of TLIP, but you take an intermediate output, it'll be of size 7. This is your time information. This is your embedding information, or C. So it's a pretty short sequence length. Now, in this layer, they have this group norm with a convolution, and then they reshape it so that it is not C by HW, but they flip this so that it's HW by C. And then this is basically your sequence, like in attention is all you need. So then you do a layer norm and self-attention, just like you normally would. And this cross-attention block is also just like normal. So this part here is just a decoder block in attention is all you need. So this layer norm here, or you have a layer norm and then cross-attention, where cross-attention is from this text embedding. And specifically, so self-attention is normal self-attention. Cross-attention, you have the queries are from the input information, but the keys and the values are from the conditional information. And the reason you do this is because you want your output shape to be the same as your input shape, but your conditional information has a sequence length that is different than your input sequence length. So you kind of want to play around with the shapes to make sure it gives you a good output, or it gives you the correct shaped output. Now, if you do query key transpose, then your matrix will be of shape, it'll be C by 77. And then whenever you multiply that by the values, which are of shape 77 by, we'll say C, so we'll call this C here. This is so 77 by C. Then you get out so it'll multiply along these 77 dimensions. So you would multiply this by your values, which are 77 by 768. So that would be some block, which is 77 by 768. I don't like doing it right here. I'm going to move that down. There we go. No. This is 77 by C. And then that gives you your output, which is, this is C, which is then C by, no, that's not, this is T, my bad. T is this here. I'm going to call that T, the height and width, and then that's C, yeah. So this will be T by 77. And whenever you matrix multiply these together, you then get out T by C, which is what your original matrix was. It was T by C. So specifically making your keys and your values, your conditional information, allows you to get out the proper output shape. And it does the conditioning really well, which they find. So yeah, that's just cross-attention. And then the last feed-forward layer, they upscale by, so they do this weird thing where they upscale by a factor of 8, and then they split this. So like you have this vector here, which is of shape C, and then you project it to, say, 8C, and then you split it into two parts. So this would be 4C, and this will be 4C. And only part of it goes through a GLU layer. And then you concatenate you multiply these together to get out an output that is of shape 4C. 4C, and then you throw this through a linear layer to project this back to C. So kind of an interesting feed forward layer, not what you usually see where this is projected to 4C and you don't have this split here, but kind of an interesting approach. And then they reshape this back to flipping back to this dimension here, and they do an output convolution with the residual from the input to the output. So that and unit is just a bunch of these together. So this is our residual layer, and this is our attention, cross attention layer. And you can see here, it's just a bunch of those over and over again. And I thought it would kind of be interesting to look at the self-attention architecture because you never really get a chance to kind of look at it, but they have some nice diagrams here that show how it works. Now, finally, onto the distilling part, which is what you were probably looking for here. But yeah, the way they distill this is by removing blocks. So we'll look at the first one, the base, and they remove all the orange blocks. And the orange blocks are the second blocks in the downsampling layers, as shown here. So all the second blocks, and the middle blocks of the upsampling layers. Right here and right here. So specifically, it's just they're basically removing a chunk from each of the up and down blocks. And they mention up here why they do that. They say, go here. For the down stages, we maintain the first RA pairs, so residual attention pairs, while eliminating the second pairs, because the first pairs process the changed spatial information and would be more important than the second pairs. Yeah, so it's so whenever you do a single downsampling layer, this is the first block is the one that processes that downsampled information. Well, the second block just reprocesses that information. So they argue that the removing the first block would not be would be a lot less beneficial. Like it needs to do a lot more processing than the second block. And they also say that for the up stages, while adhering to the so they retain the third RA pairs, and they also retain the first RA pairs. The reason they already mentioned why they retain the first RA pairs, but the reason they retain the third RA pairs is because it allows them to utilize the output feature maps at the end of each down stage and the corresponding skip connections between the down and up stages. So the output features they also argue are as important as the features being processed in the input. So you don't just want to have for the upsampling, because the output RA blocks kind of prepare it to be upsampled again. So that's what they argue here. I'll change back to this. And that's why if we go back down here, you can see that they only remove the middle blocks and the second blocks in the downsampling. Now, to make this even smaller, they can remove the entire middle part. Let's go back up here. And they say, so you can remove the entire middle stage. Surprisingly, removing the entire middle stage from the original unit does not degrade the quality for text prompts while effectively reducing the number of parameters. And we'll look at the results in a second, the results in ablations, but they say that if you remove the entire middle block, it does harm performance, but it doesn't do it as much as you would expect. And it's a good trade-off because removing the entire middle block removes a lot of the parameters. So that's a good improvement if you want to get even smaller. Now, even smaller, they call this tiny. You remove orange and pink. So this pink part here means that they basically remove the middle part along with an extra up and down sampling layer. So instead of it being 4 layers, so 1, 2, 3, 4, it's only going to be a 3-layer unit. So they basically make it more shallow without a middle block if you want to make it even smaller. And they also remove the blocks here. So this is going to be a really, really small unit. You basically only got a few downsampling layers and a few upsampling layers. So that's what they propose to just to make it smaller. Now you can't just remove the blocks. You have to do some more to it. So you actually have to train the thing. Now the way they train this is they use a 3-part loss. So the first loss is just the reconstruction loss, as shown here. So they just train this like you would normally on a data set of text and image pairs. So you have your conditioning text y, and all you do is you noise the image to some time step t, and it predicts the noise. And you just train it to predict the noise in the image. So you have this smaller model, and all you're doing is you're having it predict the noise at any time step t along the diffusion trajectory. Now, they don't just do that. They have 2 other losses, which you would kind of expect. You're doing knowledge distillation, so you would expect a knowledge distillation loss. And this loss is just saying the output of the teacher, which is your large stable diffusion model, should match the output of the student, which is your small stable diffusion model. But additionally, they say that the output of each block, the output of each layer, so if we go down here, the output of this layer should be the same as the output of this layer in the smaller model. Like, you can't do a one-to-one comparison within each of the within each of the like residual and attention blocks, because they may have different features. But what you can do is you can match the features of the outputs of each of the down and up sampling. So you can do feature matching as opposed to just saying it should have the same output. So they have these 2 extra losses here, where this loss is just the output of the student and the teacher should be the same, and this loss here is the output of the intermediate parts of the student and the teacher for all layers L should be the same. That should also be minimized. And they find that adding these 2 losses helps. So this is your final loss, and this is your output matching loss, and this is your feature matching loss. And they have these lambda values, which they just make 1. The lambdas for the knowledge distillation are just 1. Now, yeah, so let's go over to the ablations, because I think that's how you can get like the big idea of what these changes do. So the first thing they note is importing the pre-trained weights for initialization clearly improves the performance. So you can't, if you start from a random network, so you remove all the blocks and you just start from a random initialized network, it does a lot worse than if you do a pre-trained network, as you can see here. Now, the next thing that they point out is the output level knowledge distillation boosts quality, but also the feature level knowledge distillation improves performance, which is shown here. So if we add knowledge distillation, just the output knowledge distillation, then it improves performance, but you get even more performance boost if you add feature level knowledge distillation. Now, one interesting thing that they point out, like you wouldn't really expect this, is if you increase the batch size, it actually increases the fidelity, the FID value. And it's kind of counterintuitive because it also, like, it increases the clip score and the inception score, but a lower FID is better, while a higher clip and inception score are better. So the FID gets worse, while the inception and clip scores get better, which is kind of counterintuitive if you just increase the batch size. So that's something interesting that they point out. And finally, they point out the models N6 and N7 with the mid stage removed have way fewer parameters, so 0.66 billion, than the N4, N5, 0.76 billion, offering improved computation efficiency. So N4 and N5 have no middle stage removed. But if you remove the inner stage, so this is just removing, this would be small, where you just remove the middle stage, then you can see like the quality is not that much worse. It's still very, very close. And if you remove the middle three stages, meaning that your UNet is one block shallower and it doesn't have the middle stage, this would be your tiny model, then it's still not that much worse. But if we don't remove any of those stages and we just do the normal block removing, then this is the performance they get. And it's very close to the original Stable Diffusion performance, which is interesting. Now, yeah, so this would be, yeah, so that would be your 3-stage removal, and then just removing the block would be your 1-stage removal. So yeah, they also have some more results here, but I think that covers it down there. I want to find where do they say how much data they use? Here we go. So despite being trained with only 0.22 million samples and having fewer than 1 billion parameters, our compressed model demonstrates competitive performance on par with previous large pre-trained models. So they only use 0.22 million samples, and that means you can train this fast and on a small GPU, which I think they only train on one GPU. I highlighted that. Do not know where. Yeah, so I think they just train on one GPU, and it doesn't take them very long to train. Yeah. But yeah, so they basically just use a small data set, and you can make your model a lot smaller by using this compression technique, where you remove some of the blocks, leave them initialized, and do knowledge distillation. Now, finally, I think it's interesting to look at some of the results that they have. So they also do Dream Booth if you're interested, and the Dream Booth actually does pretty well. So I guess we can look at the Dream Booth results first. If I scroll up here, make this larger so we can see. So this is some of their Dream Booth results. Dream Booth, what you do is you take an input subject. So this is your input subject here, and you kind of make the model generate images within that for that subject, and you can prompt it with text to so in this case the prompt would be like a identifier class noun, so it's like yeah, so AV dog or something like that, AV stuffed animal. So whatever, maybe you say like they have here a dog in the jungle or a stuffed animal with the Eiffel Tower in the background. So that's what they use. And your V token is your special token, which allows you to generate this particular subject in the image. So that's kind of what you do at Dream Booth. You take an input image and you kind of force the model to only generate different styles of that image. So in this case, it would be that specific dog in the jungle or this specific stuffed animal in the Eiffel Tower with the Eiffel Tower in the background. And you can see that it's pretty similar. The small and the base model, they do pretty good while being a lot smaller. So yeah, this image here, I mean, it's very similar. It gets like the wave texture in the background. It gets the stuffed animal texture as well. So it's pretty good. I guess the blurring is a lot better in this one. But Dream Boost still works pretty well. This is another example where you have Stable Diffusion, and that's the base model, and it's still pretty good. The tiny model is not as good. That's the input, and that's the I guess that's your input salad for Dream Booth. Now, results on without Dream Booth are still interesting to look at. So here's Stable Diffusion 1.4, and here's the base. Now, is this Dream Booth? Yeah, this is not Dream Booth. Good. So this is just prompting the model with a bowl that has vegetables inside it. So if we just look through the images, I mean, they look completely fine. They look good. I mean, the tiny model doesn't do too well, but the base and the original, they are very similar in performance, which is what you want to see. So if we just look at a few of these. Yeah, so here's another example what they showed. So here is the base with batch size 64. This is without knowledge distillation and random initialization, and this is without knowledge distillation but a pre-trained initialization. And the results with a random initialization are just terrible. And I guess it's to be expected because your model isn't trained on a lot of data. So it can't do that well because it's not trained on a lot of data. But this pre-training it, you have to do your pre-trained in it to get somewhat decent results, and knowledge distillation improves it even further. There's a very big difference between the knowledge distilled model and the normal score matching or normal noise matching model, which is kind of cool to look at. So yeah, I mean that's all. Those are all the results. I think this is kind of a cool paper to see how you would do this for a convolutional neural network, as opposed to how you do this with a text network, a transformer, because it's very different. How you would have to do this, but overall pretty interesting. Curious to see if this works as well as they say it does. I think Hugging Face recently implemented this, so be kind of cool to check out. But anyways, there you go. BK-SDM.